Assalamualaikum and a very good day to everyone. My name is Mama Ashraf and today with my partner Rashid, we will be presenting on Mini Project for Energy and Process Utility Engineering subject for September semester 2024. Let's take a look at the project overview. The first part of this project is the overall process of residual oil hydrogenation plant in general. Next, we will be talking about the type of furnace and cooling tower used in the plant with its purpose. Next, we have the operating condition of furnace and its capacity. After that, we will find out the maximum inlet and outlet temperatures of cooling water for each process coolers. And the last part, we will have a discussion on cost saving. This is the process flow diagram for overall process of residual oil hydrogenation plant, where the purpose of this process is to remove harmful substances from the residual oil feed, such as sulfur, nitrogen, and heavy metals. This process is typically positioned in the middle to later stages in refinery product chain to provide high value added product through the deprocessing and transformation of raw materials. The sequences of this process begin with the oil phase of the atmospheric tower buffer tank is pressurized by the tank bottom pump before entering the atmospheric tower heating furnace. The feed is preheated to 187 degrees Celsius using heat recovery heat exchangers before entering the heating furnace. The raw materials are heated to 313 degrees Celsius in the heating furnace before entering the flash section of the atmospheric tower. The outlet temperature of the heating furnace is controlled using a fuel regulating valve. Part of the distillate oil in the atmospheric tower is extracted and sent back to the tower after heat recovery through heat exchanger and the sideline reboiler. Atmospheric wax oil is often sent to heat exchanger for heat recovery by the bottom pump of the tower. Finally, the residual oil is cooled to 153 degrees Celsius and sent to the wax oil hydroheating unit for next stages in the refinery process. Let's take a look at the type of furnace. There are two types of furnace that we learn in the Energy and Process Utility Engineering subject, where the first one is direct fired furnace and the second one is waste heat recovery furnace. The difference between these two furnaces is the first one use heating source to directly heat the working fluid, while the latter use the waste heat recovered from other process to heat the working fluid. In this process, I believe furnace that F501 is the direct fired furnace because the residual oil feed are directly heated to 312.68 degrees Celsius. F501 is the primary heating source for oil feed before entering the atmospheric tower.
Assalamu alaikum, I'm Rashid. I will briefly explain the proposed cooling tower type and its purpose. In this plant, there hasn't been used any cooling tower. However, from the process flow diagram, it can be noticed that there are two utility coolers with a thermal load of 58 gigajoule per hour. We recommend the counterflow forced draft cooling tower because it's highly efficient for handling large heat loads in process plants. Its design ensures effective heat rejection where air moves counter to the water flow for maximum heat transfer. Additionally, this type is compact, has high cooling capacity, and provides precise temperature control. The primary purpose of cooling tower is heat rejection, where heat from the cooling water is evaporated and released to the atmosphere. This helps maintain cooling water at optimal temperature, supporting process coolers to work more efficiently. By reusing cooled water, the system also reduces the need for additional utilities, contributing to the energy efficiency and cost savings. Overall, the counterflow forced draft cooling tower ensures minimal energy consumption, aligns with the energy optimization goals, and significantly cuts operational costs.
Let's talk about the operating conditions of F501 and its capacity. According to the data obtained from the literature, the operating temperature for the furnace is 400 degrees Celsius with the operating pressure at 3 to 10 bar. The capacity for the furnace can be from 20,000 to 200,000 barrels per day. To determine the maximum inlet and outlet temperatures for process cooler, first we have to identify the cooling water base cooler exists in the PFD. According to the PFD, only A506 is the cooler that utilizes cooling water as the working fluid to reduce the temperature of the oil feed. The inlet temperature of the oil feed is at 152.84 degrees Celsius, while the outlet temperature is at 82.91 degrees Celsius. By assuming the minimum temperature difference delta T min equals to 15 degrees Celsius, the maximum inlet and outlet temperature of cooling water can be found out, where the inlet temperature of cooling water is equals to outlet temperature minus delta T min, and the outlet temperature of cooling water is equals to inlet temperature minus delta T min. Therefore, the inlet temperature of cooling water is equals to 77.91 degrees Celsius, while the outlet temperature of cooling water is equals to 137.84 degrees Celsius.
Moving on to the cost saving, I will be discussing the cost saving achievable with an appropriate furnace and cooling system. Let's first look at the furnace. High efficiency furnaces can reduce fuel consumption by 15 to 20%, and integrating waste heat recovery, such as economizers, saves an additional 5 to 10%. This optimized fuel usage translates into substantial savings on energy costs. Furthermore, automated systems minimize wear and tear, reducing maintenance expenses by 20 to 30%. Efficient furnaces also emit fewer pollutants, helping us comply with the environmental regulations and avoid penalties. Now, moving to the cooling system, efficient cooling towers can cut electricity usage by 20 to 30% with advanced motors and variable speed drives. Optimized water usage saves another 10 to 15% annually. Better temperature control improves the efficiency of the downstream equipment, while stable cooling reduces thermal stress, extending equipment lifespan, and lowering replacement costs. In summary, selecting the right furnace and cooling system not only boosts efficiency but also significantly reduce operational costs, making it a critical step towards sustainable and cost-effective operations. That's all from us. Thank you very much.